All right, so as we just start kind of talking through sampling distributions, let's take a look at sampling proportions. So at the end of this, the objective is to be able to describe how sample proportions relate back to the population, right? Uh, we have some population of interest out there. We take a sample, and from that sample, what we're going to do is we're going to get some kind of proportion, some kind of p hat. And if that's a good p hat, then we're going to say, all right, we think this is what the population proportion would be, which would just be represented by a p. So take a quick example here, excuse me. This research company uh, talked to 400 likely Democratic voters. So there's your population of interest. We're the 400 Democrats, right? The Democratic voters, there's your population. The 400, it's kind of hidden there. I don't know why that popped back in the way. The 400 likely voters, those are the ones, that's your sample. And then we get a p hat, excuse me, that 49%, that's of the sample, so there's your p hat. But if you notice down here, once the primaries were over, we knew the true percent that favored Obama was 56%. So there's your true proportion. That's your population proportion compared to your sample proportion. So what we're going to start to look at is we're going to start to try to kind of see how good was that poll. They were 7 percentage points off, right? It should have been, right? Poll should have been close to 56 for to 56%. Should have been close to 56%, but we're 7 percentage points off. Right? The question for us, at 7%, is that a big deal, right? So another way to think about this, we can start to do some probability calculations when we start to think how likely is it for that company to get 49% when the true percentage was 56%. And the way we're going to do that is using a sampling distribution. So a way to think about this, um, if we were to just start taking a bunch of samples of 400 voters, um, obviously here's your 0.49, uh, 0.5. If we thought about doing things this way, um, if we started taking samples of uh, these 400 person samples, right? If we did samples of 400 people over and over again, obviously the first one there was down here at 49%. But if we did another sample of 400 people, we might get a 53%. Another sample might give us 56%. Another sample might give us 58%. We go find another 400 people and we get 56. Oh, I repeated 56. I'll fix that real quick. All right, so this would be 57, 58, 59, and maybe all the way up to 60. But if we kept taking samples over and over again, we're going to get different results along the way, right? Some of the samples might actually give us the exact 56%. We do another sample of 400, we get 52%. We sample again, we get 54%. We sample again, we get 58%. We sample again, we get maybe out here at 60. We do another sample, we get 51%. So each sample is going to probably yield a little bit different number, especially with 400 people. But what we should start to see is that these proportions, as we keep taking samples over and over and over again, they should start to take on a very familiar shape to us, the normal distribution. So what we're really after, this right here is what the proportion's supposed to start to be. What we want to kind of take a look at is we're way down here at 49%. Is that significant enough that it would cause us to question what's happening? So what we're going to start to see are these sampling proportions will stack up in a normal distribution. And what they're going to stack up around is they're going to start to stack up around the true proportion. And the standard deviation for this will be PQ over N, right? Keep it in mind. P hat, that's the sample proportion. So each time we took a sample, we got a unique proportion. And then P is what we think that the population proportion is. Or in this case, we actually know that it was 56% once everything was over. Okay. One thing we have to be aware of, though, there's certain conditions that must be met. First, we want to make sure that our sample was taken from a simple random sample, or that randomness was involved. This is a gold standard as a SRS. Two, we want to make sure this is a test for independence. We want to make sure that the observations aren't causing some kind of reaction, right? We want to make sure that the first voter we talk to doesn't affect the second voter. And the way that we can do that is we just want to consider, is the population that we're interested in, is that at least 10 times bigger than the sample? Basically, making sure that that the population is big enough that each individual isn't going to be affected by someone else, right? And then the third one, here's something to realize. With all these proportions, just as a reminder, these are actually coming out of a binomial distribution, right? They either voted for Obama or they didn't. That's a binomial distribution. Okay? That's something to be aware of. So that third condition, if you remember back, to do the binomial distribution, to do a normal approximation, because that's what we're going to do, right? These are starting to stack up to be normal distributions. If you recall, the normal approximation of a binomial, we have to have NP that is greater than or equal to 10 and NQ is greater than or equal to 10. So here are the three things that we're going to check every time that we do these problems with proportions to make sure that we are in fact following good procedures. One thing I do want to point out too, that's just the P, not P hat. And remember that P is the population proportion. So let's go back to this question. What we're really looking at, was this poll, was there something strange with it, right? They got 49% using their poll when the true proportion was 56. So we're basically going to look, was the probability that we got a proportion of 49%, right? Could we trust another poll from this company? Is this so strange that we think something's fishy? So ready? We'll go through. Step one, we'll check our conditions. So was it taken from an SRS? It actually never said that. So we're going to assume that it came from a simple random sample. The next thing, this was talking about Democrats. So we have to consider, are there 4,000 Democrats? I would say that there probably are. And then the final thing, our N was 400, and the P here is 0.56. That is greater than or equal to 10. And then 400 times our Q value is also greater than or equal to 10. So we're going to say that we've met our conditions. So step two, let's think about what is the mean here. So that curve started to kind of stack up around 56%. That's the true P, right? The center of the distribution should be the true proportion. And then the standard deviation would be P times Q over our sample size of 400. That's about 0.02. Now, right away, we should start to kind of see, well, if we're interested in what's the probability that our P hat was so low, some of you guys are probably already realizing, well, that's more than 3 standard deviations away. In fact, if we did the z-score, right, the critical value here is 0.49, the mean is 0.56, and if we divide by the standard deviation of 0.02, we would realize this is 3.5 standard deviations below the mean, right? If we put this onto a curve, we'd realize that 0.49 is right here. So this is a very low probability. Very quickly, since this is a normal curve, we could use our normal CDF. And because all of these conditions are essentially met, we got it. So we're going from negative infinity up to 0.49. Our mean is 0.56 and our standard deviation is 0.02. And with that information, we see that the probability that we got what we got is 0.0002. That's a very unlikely outcome. If the true proportion is 56%, this might cause us to question that poll. So maybe we do get one more example, and this is an example off of our worksheet from today. So this article reporting that hepatitis occurs in 7% of blood recipients, right? So in 7% of all blood recipients. That is talking about of the whole population, right? So our population here would be blood recipients. Oh. So people that receive blood. This 7%, that's the P, right? So we have this new treatment is believed to reduce the incidence of the hepatitis. So it's given to 200 people. So here's our sample. And then only 6 contract hepatitis. So now all of a sudden we've got our P hat is 6 out of 200 or 0.03. So we got what the proportion should be and what our new proportion is. So we have to start thinking about this, right? All of a sudden we realize it's 4% lower, right? Which, again, is that a big enough deal that we would think, okay, this is a good treatment. We better change the way that we're doing all of this. So, quick look at conditions. If you look at the conditions, 1, did we come from an SRS? And it says a treatment is given to 200 blood recipients. So again, we don't know, so we're going to assume. 2, we have to assume that since our population here is blood recipients, we have to go ahead, I'm going to guess that there's more than 2,000 people getting blood. And then finally, N times P. So we got 200 people. Remember, use your proportion, your P, not your P hat, and then 200 times 0.93. All of this, so our 3 conditions are met, so we move forward, right? So we're going to try to figure out what's the probability that we get below 0.03. So our mean here, it should be 7%. Our standard deviation, because we've taken a sample, we have to divide through by the number of people in that sample. Divided by 200. So our standard deviation here is 0.018. So if we look at our standard normal curve, right, we should be up here, right? The curve centers around 0.07. We're kind of interested in, well, what's the probability that we get down here, right? So, excuse me. So let's quick z-score. You might have already seen that. So the critical value for us is 0.03. The mean was 0.07, and we just saw that our standard deviation was 0.018. So how many standard deviations below the mean are we? Oh, excuse me. We are 2.22 standard deviations below. So is that stringent, right? Are we far enough away? So very quickly, we'll just look at our normal CDF here, and we're going from negative infinity. So again, keep in mind they were up here 0.07, 0.03, so we're not quite 3 standard deviations away. We're sitting somewhere between 2 and 3 standard deviations away at 0.03. So we'll go from negative infinity to 0.03. We're centered at 0.07 with a standard deviation of 0.018. So go to the calculator very quickly. So negative infinity up to 3%, our mean of 7%, and our standard deviation of 1.8%, and that is 0.013. So a way to think about this, there's basically a 1% chance that only 3% of people get hepatitis using the new method if 7% of people were supposed to. So that would lead us to believe that maybe this is a pretty effective treatment, right? The fact that there's such a low probability that we got our results if 7% of people were supposed to.